Hey everyone, I hope you can hear me clearly. We'll just give another minute or so and then get started. So while we are waiting, I can just kind of cover the logistics again. So, if you raise hand, there's really no way I can give you permission to speak. So all questions you should raise through the Q&A. And if it's just a logistical issue, you can also post it in the chat, but I'll monitor the chat only at the very end. And as I speak, feel free to add your questions to the Q&A. I'll pause every couple of slides and take a peek at the questions and see what I can answer, while sticking with the flow. And things that I can't get to right away, I'll try to get to it in the 5-minute break in between or at the very end. Yeah, so there are some questions about the slides being available. So I think the slides are already in the download area, or they might be linked on the HiPEAC program. Yes, if you do have questions, you're welcome to email me anytime. And my email address is rajeev@cs.utah.edu. And so I'm happy to entertain some questions as well over email. Okay, all right. So let's get started. So this is the third and the last lecture in this series, and so I'm going to cover a few things that might be that are more challenging and maybe on the roadmap for future accelerators. And so in the first couple of sessions, right? So on Monday we just covered the basics of what these deep neural network workloads look like, and we did a tour of some of the first commercial designs that are already kind of that are growing in popularity and have influenced much of our thinking. And then in yesterday's lecture, I kind of focused on what might you do to improve efficiency of these initial accelerators. And so we had a discussion of data flows, and we covered 4 or 5 different data flows, including the ones that already are commercial and the ones that have been published in research papers. And then we looked at other potential opportunities, and I said that one of the main opportunities out there is the fact that there is a lot of ineffectual computations happening in a deep network. And so can we identify that and somehow avoid the time and energy that we spend processing those ineffectual computations, right? And so we looked at sparsity, which is a special case where if a value is entirely 0, then you don't have to store it, you don't have to do any computations with it. And then we looked at a couple other examples where when specific bits are 0, can you avoid those computations? If you realize that there's redundant computations, can you get rid of them? Right? So that's kind of what we focused on Monday and Tuesday. And some of our main observations is that the data flow is really important. That's an inherent property of any architecture. And there may be the potential to come up with even better data flows in the future. And we saw that the first generation accelerators have already caused a huge 100x improvement in performance. And this is mostly because they were able to pack several Mac units onto the chip. They have primarily used systolic data flows to reduce the energy cost of all the data movement. And in the next generation jumps, right? So trying to exploit sparsity is not as easy, right? So there are some low-hanging fruits where you can get a 10x improvement with not a huge cost in terms of design complexity and metadata. But then there are several other innovations where the improvement may only be about 2x, and the corresponding complexity is also a lot higher, right? And so I think the next generation jumps are going to be much harder to get. We also discussed in the very first class that that DNNs themselves are evolving to be smaller, right? So people have realized that reducing the connections within a convolutional layer can not only make it faster to train and make the network more accurate, it also reduces the storage cost. It also reduces the overall computations required, right? And so even the DNNs are moving in a direction where they might be more compact naturally, and that further helps these accelerators, right? And so in today's discussion, I'm going to look at things that so this is keeping with the theme of what are the potential next steps these accelerators might take. And so I'll start with the discussion of in-memory processing, which is a little further out there, right? So these are not commercial yet, but they may be worth considering for second and third generation accelerators. Then we'll also talk about training, right? So until now, our discussion has mostly focused on inference, which is the easier problem. Training is basically inference multiplied by 3 plus additional memory, right? And so it's a little bit more complicated. And there are fewer startups looking at accelerators for training, right? And so we'll discuss what it takes to augment our accelerators so they can handle these training workloads as well. And then finally, I'll end with a discussion of spiking neural networks, which are not super fashionable today. But who knows, in the next 10 years, maybe that's where we'll see our biggest jumps in terms of innovations. Okay, so let's get started, and I'll first focus on in-memory processing. And there are many. So when we talk of in-memory processing, this processing can happen inside SRAM storage structures, inside DRAM, inside non-volatile memories, and I'll do one example of each of these. Okay, so let's start with SRAM. So here's a circuit that came out of a group in Michigan, and I'm sure there are other groups as well looking at these kinds of circuits. But I'm specifically focusing on the compute cache and the neural cache papers that came out of Michigan in 2017 and 2018. And so in what they're advocating is to basically look at the large SRAM structures that already exist in modern CPUs, and saying that with a little bit of addition, with a little bit of circuit additions to the SRAM structures, you can perhaps do some simple computations within each SRAM bank itself. Okay, and so I'm kind of showing you what the key insight in their circuit is down here, right? So in these SRAM circuits, you have rows and rows of cells. You have a word line that travels in the horizontal direction. It activates all the cells in a row. And then the values of those cells are then placed in bit lines, right? And in SRAMs, you have a bit line and a bit line bar, and you have a differential sense amplifier that detects the difference and amplifies that difference. And so in their proposed circuit, they're essentially saying that if you turn on 2 word lines at the same time, one of the bit lines is essentially going to carry the AND of the signals in those 2 cells, whereas bitline bar is going to carry the NOR of the 2 signals, right? So as you can see in this example, right? So this bit line over here is connected to both of these 2 cells because both of these word lines have been activated. And so what this sense amplifier is sensing over here is essentially the AND of the values of these 2 cells over here, right? Whereas the bitline bar line down over here is sensing the NOR of those 2 signals. Okay, and so at the same time, you have one line carrying the AND of A and B, and the other one carrying the NOR of A and B, right? And so instead of letting the sense amplifier do its usual thing and detect the gap between those 2, they have a new sense amplifier circuit that individually senses, what those 2 lines are, right? So essentially, by turning on those 2 word lines, you can get the AND and the NOR of 2 entire rows, right? So the bitwise AND and the bitwise NOR of the contents of 2 entire rows, right? And so starting with that, you can kind of build more complicated circuits, right? So that's kind of the key insight over here, that you can activate 2 word lines, you can change the sense amplifier circuit. That gives you access to to 2 different logic gates. And again, one of the key insights over here is that by just doing one single operation, you're able to perform bitwise and NOR of all the cells that are in that row, right? So if a row has 1,000 bits, you can do 1,000 operations in parallel, right? And so it's that parallelism that gives it its biggest benefit. Okay, so with that basic circuit in place, what can we do, right? So essentially, you can do add and multiply and other operations, all building off of the AND and the NOR circuits. Okay, so here's how they propose to do addition in this case, right? So if you see in this example, you'll see that there are many different words, right? So words 1, 2, 3, and 4, and they're organized in what is referred to as a bit serial format, right? So essentially, the first bit of word 1 is placed over here. Let's call that row number. Let's call that row 4. The next bit is placed in row 3. The next bit is placed in row 2, and then row 1. Right. So each individual bit of the word is being placed in a separate row, right? And so here's the vector A, and then here's the vector B, right? So this is just an example that's showing 4-bit addition. And so when you want to add vector A and vector B, it's basically this bit that has to be added to this bit of, so the 0th bit of A has to be added to the 0th bit of vector B, right? And so essentially you activate both of those rows at the same time, and then you get the AND and the NOR, and then you perform all the additional logic that you need to produce the sum and the carry out, right? So the carry out is stored in a latch that is next to the sense amplifier, whereas the sum gets written back into the SRAM cell. Right, so essentially you have the result that is produced, and then you use a normal write operation to write the result back into one of these rows. Right, so that's these rows over here that are reserved to store the outcome of your addition. Okay, and so in the first cycle, you're basically doing 2 rows that allows you to add the least significant bits. In the next cycle, you'll read the next 2 rows that lets you add the next significant bit, and so on. Right, so if it's 4-bit addition, after 4 cycles, you've produced all of your results, right? So if it's n-bit addition, that's going to take n cycles. There's quite a bit of SRAM reads and writes involved. Not as much reading and writing out of registers, which is kind of what we had said would be very valuable, right? So when we discussed data flows, we basically said that there is this hierarchy that feeds the MAC units, and you ideally want to get your data out of registers and maximize reuse. If not, then you go to the next level, which might be a few kilobyte buffer. If you can't find data there, then you go to the next level of the hierarchy, which may be a few hundred kilobytes or megabytes, and then finally DRAM, right? But over here, you'll see that all the operations are being fed with these SRAM reads and writes, which are a little bit more expensive. But the good news is that every time you do a read or a write, you're accessing an entire row, right? So you're actually feeding a number of different operations all at the same time. Okay, and so it seems a little time consuming. It seems like every single operation is requiring so many SRAM reads and writes. Just doing one addition required us to do 2 n reads and n writes, right? And so the main reason why this ends up being effective is because of the very high parallelism, because you have so many bit lines that are kind of that are working in parallel. Okay, so that's kind of the main benefit. So let me just kind of pause for a second, see if there are any questions. So there's a question about, isn't there a possibility of modifying stored data? So, and there's a question that relates to DRAM, right? So this first circuit that I'm talking about is only focused on SRAM, right? Which is not a volatile cell, right? Because of the feedback loop. When you read something, it's not a destructive read. The sense amplifier does have to be modified. So I think on the very next slide, I talk about the few changes required to the sense amplifier. And so essentially, yes, the circuit does need some changes in order for this to work well. But there is not the concern with destructive reads as there is in DRAM, right? So the next design I'm going to talk about is DRAM operations, and there, yes, the operations are destructive. Okay, but here that concern does not exist. So yeah, so so here's where I talk about kind of the change to the sense amplifier, and I'm not going to get into the circuit, but what is important to note is that, yes, this is a different sense amplifier. As you said, you have to avoid, disrupting the values of the cells, because, you're accessing multiple cells, and they're, both feeding the bit lines. And so you have to operate at a lower voltage, operate at a lower clock as well, right? And so again, all of that makes it seem like you're losing some performance. But again, keep in mind that you can make up for that performance loss with just higher parallelism. Okay, so a lot more details over here. Again, I won't go into all of this, but one of their arguments is that if you have an existing CPU with a large cache, this is an easy way to to add some functionality to each cache bank, and say that in addition to being a CPU, this can also do in SRAM bank processing, and it can handle these deep neural network computations, and you're able to do it with just a 7% area overhead per subarray, which is a small fraction of the entire chip. Okay, and so the elephant in the room in some sense is that what I just described to you was just addition. Multiplication is a lot more complicated, right? And so multiplication requires n-square computations, right? And so if you're multiplying two n-bit numbers, you have to do order n-square such additions, and so that takes a lot more time, right? And so multiplication is a lot slower than the slow addition example that I just showed you. Right, and again, it's the same story where if you have enough bit lines operating on this in parallel, then that turns out to be a worthwhile trade-off. Okay, and so that's kind of what the neural cache does, and it's basically putting compute into SRAM, and it requires some changes to the sense amplifier, but it allows you to do simple AND and OR operations. Okay, so now let's switch gears and talk about DRAM. And in DRAM, you have even more bit lines available, right? Because SRAM structures are usually a few megabytes in size, or tens of megabytes in size in most chips, whereas DRAM is many gigabytes, right? And so you have many more bit lines in DRAM, and so you should be able to get even higher parallelism, right? So that's the main motivation for trying to do in DRAM computation. And like was already mentioned in the first question I answered, you have to deal with the fact that DRAM cells, have destructive reads, right? When you read something out of the DRAM cell, the charge in the capacitor actually gets placed on the bit line, and that charge is lost. And so, as a result of that, when you're doing computations involving DRAM cells, you have to first make a copy of the row, right? And so, this is almost like a pre-processing step, right? So before you do the actual computation, you make a copy of the row if you want to still hang on to it. And obviously, things like weights, you do want to hang on to it. And so if you first make a copy, and then you can perform this operation, right? And so it's a slightly different circuit. So in DRAM, just as with the SRAM case, you're activating multiple rows. And in the case of DRAM, there are 3 word lines that are activated, right? And so there are 3 cells in every column that are going to be connected to that particular bit line. And the value being sensed over here is the majority of those 3 values. Okay, and so you can basically put operand A over here, operand B over here, and the third row can be either all ones or all zeros, right? So if I put this as all ones, that essentially turns this into an OR operation, right? So if either A or B is 1, then the majority is going to be 1, right? And so the logical result that you get on that bit line is OR. Instead, if I make the third row into a 0, that turns into an AND circuit, right? The output is going to be 1 only if A and B are both 1, right? Then it wins the majority. Okay, and so you can kind of set that third row to either be all zeros or all ones. Accordingly, you can get a result that's either AND or that is OR. Okay, and then there are there are different implementations as well, but this first circuit I think was relatively easy to explain and understand. So I'm just describing that, but you can create other circuits as well. And you can look at the Drissa paper for more details, right? And again, they show pretty significant improvements. And again, that improvement is a function of how much DRAM there actually is in the system, right? So of course, if you have more DRAM, you can get even higher parallelism and even higher performance. Okay, and so I just want to end this discussion by mentioning a couple of, the discussion on SRAM and DRAM. With a couple other papers that I think are worth looking at, or are good starting points if you want to study this even more deeply. So Compute DRAM is a paper that appeared at Micro 2019, and essentially says that we already have DRAM parts where you can kind of violate the timing parameters, and you can already fake some of these operations or emulate some of these operations. It's not going to have very high, it's not going to be a very reliable operation because, you know, in some sense, you're hacking the chip to do things that it was not designed for. But again, you know, these neural network operations can perhaps tolerate noise. So it may be a worthwhile experiment to see if you can run real applications on off-the-shelf DRAM parts, you know, and by faking these timing parameters and seeing if you can actually do these operations, right? So that's so the Compute DRAM paper basically said that this is possible, but I think, you know, more needs to be done to show that real applications can actually exploit it. And then, of course, there is the other approach that says that, you know, you can have 3D stacked memory, just like in a hybrid memory cube, where you can put computation, you know, close to memory that kind of reduces the or lowers the memory wall. And so the NeuroCube paper, which I think was ISCA 2016, so that paper essentially showed that, you know, there's a pretty good benefit to be had there. Okay, so let me again just pause for questions. Yeah, so so somebody has asked about the copy process in DRAM, and yes, that is a significant overhead, right? And so again, you can copy in several banks in parallel, so the latency penalty may not be as high, but it does cost energy, and as you note, it does eat into the capacity as well, right? But, you know, many of these models are a few tens to hundreds of megabytes in size. Even the feature maps that you produce along the way are, you know, hundreds of megabytes. And so, you know, that's well within the capacity of most DRAM systems. So it should not be a problem. Somebody had a question about, does the wire operate as an AND, right? And so, yes, that's essentially what is happening, right? So, you know, when you have multiple cells, multiple DRAM cells connected to the same bit line, right? Some of the cells are adding charge and some of them are essentially acting as a ground. And so, you know, people have empirically shown that, you know, that depending on what the majority cell is doing, you know, you're going to get that majority result, right? And so we are essentially setting the third cell to a value that then allows us to kind of, you know, implement an AND or an OR, right? So it's basically saying majority of 0, A, and B gives me an AND. Majority of 1, A, and B gives me an OR, right? So that's essentially what's happening there. But yeah, the wire is kind of operating not as an AND, but as a majority extractor. So this third question is saying, you know, are we using near memory approaches instead of a dedicated accelerator or integrated into, right? So, you know, so many of these early papers are somewhat agnostic to that choice, but, you know, they do have a vision for how you would use it, right? So at least the compute cache and the neural cache works are saying that, you know, let's take a traditional CPU. You know, you can add a separate accelerator to it, or you can just take advantage of the fact that the CPU has, you know, 10 megabytes of SRAM sitting around, right? And so, you know, putting some in SRAM capabilities can allow that general purpose CPU to turn into an accelerator, right? And you know, you could also apply that same concept and say that, you know, even on a Google TPU, you have a 24 MB SRAM cache sitting around. Right, so imagine what more you could do if there were these in SRAM operators inside that large SRAM, right? But I think most of the time people talk about taking an existing CPU and basically converting it into an accelerator. But I think that concept is generally applicable in both cases. And so what are the drawbacks of in-memory computation, and is it not mature enough yet? And so that's, I would say, one of the key issues so far, right? So this the compute cache paper that appeared only in 2017, right? And so I don't think that circuit has been around long enough for it to kind of find its way into commercial products. And yeah, so even you know, all of these papers have come out in the last 5 or 6 years. So it's not yet mature, and you know, there are trade-offs, right? So like I mentioned with the SRAM circuit, it's you know, you do have to operate it at a lower voltage. You do have to operate it at a lower frequency. And so, these SRAM arrays are so well understood, they're designed for very high density. And so it's understandable that industry will, there's always going to be a little bit of pushback in terms of, modifying what is a well-known and dense circuit. And so it all comes down to, are there enough applications that can exploit this? And, once you make that case, then I think folks within industry are willing to accept it and make it part of the products. Right. So so the main issues are, there are trade-offs in terms of complexity, power, latency, clock frequency, and so on. And so it always takes a little time for it to mature. Okay, so now I'm going to move on to the third example of in-memory compute. And this is an approach that has also spawned a few startups. And so this is essentially using non-volatile cells, and it's using analog math to do it, right? So the two approaches I described so far, right? So both DRISA and the compute cache work, they are still digital circuits, right? They're still using these sense amplifiers to kind of figure out, these logical operations. And, here's a third approach, which is basically, which is scaling up this operation to more than just 2 or 3 operands. And it's using analog to actually do the math, right? And so it turns out that, when you just connect a bunch of wires, there's a lot of stuff happening which kind of represents multiplication and addition, right? And so I'll soon show you an example of that, right? And the question that was just posed about why do I not already see this in industry, right? And so analog has an even higher barrier to being adopted, right? So analog has been there for a long time. But when you're doing general purpose computations, when you're doing, let's say financial transactions, you can't afford noise in that computation. And that's the problem with analog, right? If the temperature changes a little bit, the voltage and current changes as well, right? And so, you don't want your numbers to change as the temperature changes, right? And so that's always been a huge challenge for analog. But if you're doing neural network computation, some of that noise may not be a big deal, right? And so it may be a really good fit for implementing these DNN accelerators. Okay, so here's how you would do that, right? So let's just take, so in this example, I have 3 different wires, right? So 2 horizontal wires, 1 vertical wire, and I essentially have a resistor connecting the horizontal wires to the vertical wire. And if I apply voltage V1 and V2 to the 2 horizontal wires, it's basically injecting current into that vertical wire, right? And so if the resistances, if these 2 resistors have conductances of G1 and G2, you're basically injecting current V1 times G1 over here, right? And V2 times G2 over here. And because they're both injecting current into the same wire, that serves as addition, right? And so basically, the current equation is an example of multiplication, and 2 wires merging is an example of addition. And so the final current that you get out over here is V1 G1 plus V2 times G2, which is nothing but the standard dot product equation that we use in all of our deep networks, right? And so what we're essentially saying is, let's put our weights into these resistors, right? So the weights of a deep network are encoded as the conductances of each of these resistors. And my input image shows up as the voltage. And if I do that, then what comes out of each column is nothing but the computation for each individual neuron, right? And similarly, I can have a second column over here, which receives those same inputs, but has different weights. So G1 prime, G2 prime. And so this is the output of a second neuron, right? And so you can do a number of these operations in parallel, right? So kind of scaled up, this is what it would look like, where you have the inputs, which may be digital, right? And so those digital inputs have to be converted into analog voltages. And so you have a digital to analog converter over here. And then you have all the weights basically stored in this matrix of resistances. And then what comes out over here are the outputs of neuron 1, neuron 2, and so on. And those results then have to be converted from analog currents into their digital values. And so that's why you have an ADC over here, an analog to digital converter, right? And now you have the digital values that then propagate on, right? So this is kind of the basic circuit saying that, if you have this grid of resistances, I can do analog dot products, and you can give me a bunch of inputs. You can encode the weights as the conductances of each of those resistors, and then I can produce the result finally, right? So there are challenges with this, which I haven't quite got to, but let me just see if there are questions, right? So weight equals 1 by R, correct? Yeah, right? So yes, we are storing the weight as the conductance, which is 1 by the resistance, yeah. Okay, and so, this is a really good fit for things like memristors, which is just, which is just a trademark name for a resistive memory, right? Which came out of HP. And the good news over here is that these grids of resistances are very easy to implement. It's very easy to create a dense implementation of these, right? So if you look at exactly how this is done, right? So usually, you have a silicon substrate, you etch your transistors into the silicon substrate, and then you put a whole bunch of metal wires on top of that silicon substrate, right? So as part of placing those metal wires, you can implement these cells, right? So you firstly have, the blue wires that I'm showing you over here, which go in one direction. Let's call that the bit line. And then you're going to place the word lines, which are shown in green over here, which goes in a different direction, right? And every time you have, two of these word lines and bit lines basically kind of crisscrossing each other, the part where they overlap, over there, you implement this memristor cell, right? So you're just basically putting in some material at every intersection point between a word line and a bit line, right? So you're not kind of taking up silicon space to do this. The silicon space would have all the driver circuits and all the peripheral circuits that are required around this crossbar, around this grid of resistances. But it's fairly easy to implement these cells without taking up too much silicon area. And in fact, you can put many more metal layers, right? So you can put another layer of bit lines and word lines, and you can have another set of memristor cells that are placed in that same space, right? So it's a very scalable way to get extremely dense memory. So that's one of the reasons why this has also become very popular, because in a small amount of area you can implement many of these crossbars, right? I don't think I use that term formally, but this is what I'm referring to as a crossbar, right? So this grid of resistances. Okay, so now we get to the main challenge over here, which is the high overheads for analog to digital conversion and digital to analog conversion. So I'll just take this one question before I move on. So can the input directly be in an analog signal from a sensor? And yes, it can be, right? But just keep in mind that in any deep network, right, it's only the first input that's coming in from the sensor. And so yes, you don't need to do any conversion at that point. But if you're going through a 10-layer deep network, the results of each of those layers has to be converted from analog to digital and then back to analog again, right? One option is to keep all the signals in the analog domain. But some studies have shown that when you do that, right, every time you're doing operations in analog, you lose a little bit of precision, right? Because analog circuits tend to be noisy. And so if you stay in the analog domain, then you can't travel long distances. You can't really buffer those signals anywhere. And so the error, starts to accumulate and the end result is not as good, right? So some studies have shown that it's best to always convert from analog to digital after every single stage. Right, and then that kind of feeds into this main challenge over here, that these analog to digital converters are they're very expensive, right? They're expensive in terms of area and in terms of energy. And so if you have to do this conversion all the time, it kind of defeats the purpose, right? So, this circuit, like with the earlier examples that we saw, is very effective because it does a bunch of operations in parallel. And it does it by just simply doing a read out of a memristor crossbar, right? So you're not actually doing multiplications and additions. That just happens naturally as part of Kirchhoff's law, right? And so, there's all this efficiency advantage that you get with the read out of a memristor. But then if you have to send all the signals through an ADC, then all of that benefit kind of goes away, right? And so that's the main drawback that we have to overcome. And it also turns out that the resolution of the ADC, that really adds to the overheads, right? And so the ADC overhead, increases exponentially with resolution, right? What that means is if I'm trying to extract an 8-bit value, from the bit line, the complexity is going to be, order 2 to the 8. And similarly, if I want to extract a 9-bit value, that's going to be, twice as much in terms of energy and in terms of area, right? And so what we want to do is try to kind of reduce the resolution of the signal coming out of each and every single bit line, right? So it turns out that, an 8-bit ADC is fairly straightforward to implement. Moving to a 9-bit ADC is significantly more effort. And so in some sense, we want to stick to an 8-bit resolution. Okay, but it turns out that, this equation kind of governs the different parameters of the crossbar, right? It's basically saying that if you want to get an 8-bit value coming from one bit line, then each individual cell can only have a few bits worth of information, right? That's the W over here. The input voltage can only have a few bits of information. That's the V over here. And then you can only have a certain number of rows, right? Because the multiplication performed at every cell has to be added up across the rows, right? So if you have 128 rows, that can essentially increase the sum by a factor of 128, which means 7 more bits of information, right? So that's the log of the number of rows over here, right? And so we are essentially saying that the sum of all these three equals the resolution of the ADC. And so if I want that to be 8, that puts limitations on how large the number of rows can be, how many bits of information I can provide with every single cell resistance and with every single input voltage. Okay, and so that's the main constraint that we now have to overcome. Okay, and so the way you do it is by basically splitting the computation in terms of time and space, right? And so I don't want to provide a multi-bit voltage. Instead, I'm just going to give you 1 bit of voltage at a time, either 1 or a 0, which means the input, which could be a 16-bit input, is split into 16 steps, right? In each step, I'm just going to give you 1 bit of input, right? So that's the first thing I'm going to do, and that means that my digital to analog converter is trivial. It's just giving me 1 bit at a time, which is either 1 or a 0. Okay, but it means that I also now need 16 iterations to perform one 16-bit multiplication. Okay, and the results of each of the stages is then kind of added with shift and adds. The next thing I'm going to do is I'm going to spread the weights, right? I can't put an entire 16-bit weight into one cell because that's instantly going to make the multiplication a 16-bit value, right? And I can't have that result exceeding 8 bits. So instead what I do is I just make each cell a 2-bit value, which means a 16-bit weight has to now be spread across 8 different columns. Okay, and so that's how I'm basically splitting the weight across space, and that helps bring down the resolution of each individual cell. The third thing I'm going to do is I'm just going to have a few rows per crossbar. And so in this work, there are only 128 rows. And so if a neuron has more than 128 inputs, which is the common case, then that neuron computation has to be spread across multiple crossbars. And so again, you have to kind of aggregate the partial sums coming out of each individual crossbar. And then finally, you can have a few encoding tricks, right? And so you can either store the weights themselves, or if the weights are very large, you can store the complement of the weights. And that way you can make sure that the dot product is never a very high value, right? And so there are these encoding tricks you can do. There's also ways to handle positive and negative weights, and that's done by adding a bias, right? So I won't get into the details of how this encoding is done, but essentially you need all of these tricks to make sure that the value emerging from each bit line is relatively small. That keeps the ADC resolution small, and that keeps the ADC overhead small. Okay, so that's kind of the main point over here. So let me see if what questions I can answer. We don't need to map the input data, right? So yes, not sure I fully understand this question, but in any deep neural network, the input data is showing up as 8-bit or 16-bit values, right? And you can take that same 8-bit, 16-bit value and feed it to this network as well, right? So I don't think it changes. So going to analog has not changed the way the input data is being mapped to the different crossbars. Yeah, so yeah, this is a point I didn't quite make, right? So if weights depend on the resistance, does it mean that they have to be fixed in the design, right? And that's absolutely what I'm assuming, and I'm getting to that soon, right? And so it's basically saying that one of these crossbars is going to implement a certain convolutional filter, and so each of those individual cells has to be programmed with that particular conductance, right? And once I do it, I have to kind of leave it alone, right? This programming process, especially for most non-volatile cells, takes a fair bit of time and energy, right? So once I've programmed the cells, I just want to leave it alone, and it's always going to, it's always going to be operating as that convolutional filter, right? And so it's not fixed in the design, but it can be programmed. But that programming process is time consuming and energy intensive enough that you don't want to keep on reprogramming these cells, right? You basically keep it there, and it runs for many hours possibly. Then if you want to run a different network, you have to spend the time to kind of reprogram all the cells again. Then hopefully that network runs for a few minutes or hours, and so on, right? So you're right that this is not like with the digital accelerators that we've seen. You can't just you can't context switch different filters onto the same piece of hardware. So in some sense, the hardware is kind of hardwired to operate on a certain filter for a certain amount of time. So wouldn't all the resistors drastically increase energy consumption, right? And yes, you're right. So doing an entire grid operation does take a fair bit of energy. But when you realize that you're actually working on, if it's a 128 by 128 grid, you're essentially performing, 2 to the 16, sorry, 2 to the 14 different multiply operations all in parallel, right? So it turns out that, this analog operation consumes less energy than its digital equivalent, right? Even though that, yes, there are all these resistors that are kind of playing a role. So does analog have the same degree of challenges as it does? Yes. And clearly one of the main issues that is brought up with these accelerators is the fact that that the error rate is going to be higher, right? So when you have these sense amplifiers for these analog signals, there's a decent chance that one of these bits may be off, right? And so in fact, the very next question is, can you do error correction on this as well? And I have that coming up on a slide. And I can give a little bit more detail when I get to it, right? So, yes, reliability of your computation is important. It would be great if we could somehow, detect and correct a large fraction of errors. The good news is that neural network computations are already somewhat tolerant to noise. And so even if you don't detect all the errors, you may still get the correct result. So, this is in some sense a killer application for analog circuits, because the application itself can withstand some of these errors. Okay, but I'll give you a little bit more detail on how you might do error correction in these analog computations. Okay, so let's kind of move on here, right? And so again, I don't want to I have slides that go into more details, and you can also look at the original paper. But in some sense, I'm just trying to convey the high-level insight over here. And it kind of feeds into some of the questions that you've all asked, right? And so, here's the overall architecture. Again, it's tiled like the other examples that we've seen so far. In each tile, you have an EDRAM buffer, which stores the input and the output feature maps. And those feature maps are then fed to these in situ multiply accumulate units, right? Which essentially have these crossbars. So all the weights are already placed in the crossbars. The inputs show up, you do your computations, those results go through ADCs, they go through these shift and add operations, and then they get placed in this EDRAM buffer after an activation function is applied. Okay, and like we just discussed, once I've put some weights into these crossbars, that crossbar in some sense has been designated as the one operating in a convolutional filter 1, let's say. Right, and so you can't kind of change it. And so what we're doing here is basically saying that layer 1 is mapped to maybe these 2 tiles, right? So all the weights for layer 1 have already been placed in the crossbars belonging to those 2 tiles. Once you get the result, it gets placed in the EDRAM buffers over here, right? Which is where layer 2 is implemented. And so maybe layer 2 is larger, right? And so maybe it needs 4 tiles to accommodate all of the weights. Once it produces its result, those results go into layer 3, which is implemented over here. And so what you'll see here is that we have a spatial pipeline. Whereas in all the accelerators that we saw before, we didn't have a spatial pipeline, we had a temporal pipeline, right? So let's take the TPU, for example. So when you're executing layer 1, you have this 256 by 256 grid of multiply accumulate units, right? We were basically saying, I'm going to use all my hardware resources to execute layer 1. Once those results have been produced and stored in this buffer over here, I'm now going to move on to layer 2, right? So all the hardware resources are now at the disposal of layer 2. I'm going to make maximum progress on layer 2, produce all the results, put the results in the buffer, then all the resources are used for layer 3 and so on, right? So we have a temporal pipeline where all the resources are used for one layer at a time. And this one has changed that, and it's now using a spatial pipeline. So not all resources are being leveraged for layer 1, but some of the resources are earmarked for executing layer 1. Some are earmarked for executing layer 2 and so on. Okay, so I hope that's clear. And that's a huge distinction between these in-memory non-volatile accelerators versus the digital accelerators that we saw before. Okay. And so this is kind of that pipeline that I'm showing you over here, right? So you have specific tiles dedicated for layer 1, layer 2, layer 3, and so on. And there's also a pipeline within each one of these layers. And I won't go into the details, but you have to read inputs from the EDRAM. There are 16 cycles of crossbar operations because you're giving one input every single cycle, right? So if it's a 16-bit input, it's going to take 16 cycles. Then it goes through the ADC, shift and add, so on and so forth. Okay, and so this is kind of where I make that distinction clear that this is using a spatial pipeline and not a temporal pipeline. Okay, the other thing I should note over here is that when you have a spatial pipeline, to maximize utilization, you have to make sure that every layer has the same amount of throughput, right? Otherwise, if one stage is producing more outputs and the other stage is not able to keep up, then you end up having stalls in the pipeline, right? So essentially, you have to kind of match the throughput of every single stage, which means that if you have layer 2 over here, right? So here's layer 1 and here's layer 2. Let's say this one is producing one output per cycle. All right, but let's say that layer 2, let's say that there's some pooling happening over here, where 4 values are first converted into 1 value, which means that L1 has to produce 4 outputs for L2 to do 1 operation. So in some sense, we are asking L1 to do 4 times as many operations so that it can keep up with the operations being performed in L2. Which means that I may have to replicate some of the weights in L1 so that I can do more work in every single cycle, right? And so because of this pipeline, because of the fact that each stage may have a different throughput, I may have to end up doing some of this replication, right? So that's kind of what I thought I had it on a slide over here, but maybe I left it out. But that replication is required, and so ultimately you end up with an order of magnitude improvement over the best digital accelerators of that time, right? So this is a paper from 2016. Okay, so I'm just going to close out this entire topic of in-memory accelerators by just mentioning a few other works that have been proposed over here. So with memristors, you can do other operations as well. So there's some work out of Technion which shows how you can use memristors to also perform certain logic operations, right? So you can activate 2 rows, and just like we saw with the SRAM circuits, you can perform NOR or other operators and put the result back. People have also come up with more efficient ADCs since then. People have used the same operations to accelerate spiking neural networks as well as scientific computations. So there's all of this additional work as well. And then let me just expand a little bit more on this question about reliability. Right, so you all correctly brought up the fact that one of the major challenges here is that some of the analog results may not be correct, right? So how do I detect those mistakes and how do I improve upon them? So there was this approach from Feinberg et al., which essentially said that when you're doing these operations, let's start by multiplying all the weights by some number, let's say 17. And now when I do my dot product operation, right? So if all the weights have been multiplied by 17, when I do my dot product operation, the final result that I get should also be a multiple of 17. And if it turns out that it's not, then that means that some error has happened along the way, right? And so this is one very effective way of detecting errors that are happening in these circuits, right? So why 17? Because well, there's some theory to kind of there's some coding theory to explain why that's a good number. but usually it's some kind of prime number. And depending on the error, I can also figure out which bit line may have been wrong, right? And so by choosing 17, that improves my chances of also correcting the error, because I can tell that, there was a mistake in bit line number 3, and if I change it by 1 bit either up or down, if I end up with the result that is also a multiple of 17, then it means that I've also been able to correct that error, right? And so there are these codes that can be used to improve the reliability of this analog computation. The trade-off, of course, is that when you multiply a number by 17, now you need 5 more bits to express each of those numbers, right? And so instead of a weight being spread across 8 memristor cells, it has to be spread across 11 memristor cells. So that's the main overhead of this reliability approach. Okay, so hopefully that gives you some insight on how you can overcome the challenges of this type of in-memory analog computing. Okay, any questions? All right, so if there are no more questions on in-memory computing, I'll move on to the next topic, right? But just as a summary to take a step back, right? So firstly, why are we talking about in-memory computing, right? So when with all of these deep networks, we've already seen that the models are very large, right? And most of the energy is spent, moving those large models either from DRAM into large buffers and then finally into, smaller buffers and register files. And so in-memory computing is basically saying that main overhead can be overcome by just bringing all of those or placing all of those models in, let's say, these many crossbar, into these many crossbars. And then I don't have to move those weights anywhere else, right? The inputs basically show up over there. The computation happens inside the array. And those results basically propagate from one crossbar to the next, right? So it's basically avoiding movement of the model. And the fact that you have several of these bit lines gives you extremely high parallelism and extremely high performance. So that's the reason that we're kind of looking into this. And, like has already been noted, these are all circuits that have been proposed in the last 5 odd years. And so it's going to take a little while for them to become more mature and actually, have some appeal for industry. Okay, so I'm imagining these as potential candidates for 3rd, 4th generation accelerators, and they do have the potential to give you an order of magnitude improvement, just because the speed up kind of scales with the size of the model. Okay, all right. So I think so there's a question about, does any lab work on fully analog computation of neural networks, right? So yes, there are many groups looking at this, right? So I mentioned the group at Technion that's looking at memristors. There are groups at HP Labs that I think are still trying to push these ideas out into the commercial space. There are a couple of startups that are also looking at these analog computation, right? So in addition to the academic labs, which you can find quite a few of, I'm trying to remember the name of the company that does it. I have it in my notes somewhere, and it's just kind of escaping me right now. But if you send me an email, I can even point you to a couple of startups that are using these crossbars as the basis for their accelerators. It's something like MemLogic or something. I forget. So just send me an email, and I'll try to kind of provide that information to you. Okay. All right. So I think we are moving on to the next topic, which is accelerators and how they have to be modified to handle training. Okay, and so I'm not going to spend a lot of time on the math behind the training. Let me just try to cover it very briefly in one slide. And so I won't kind of derive each of these equations, but I'll basically convey what operations have to happen. So when you're doing training, right, so there's firstly the inference or the forward pass, right? So firstly, you're given an input image, right? You already know the answer. You already know, what the output neurons should be saying. But you give this input image, let's say, and it basically goes through the forward pass. And each of the neurons in the last layer produce a final result. Okay, and so once you get that result from the neural network, you compare it with the label, right? You know what the neurons should have said. And you essentially compute the error that's being produced in that last stage, right? Which is nothing but the actual output, which is y, minus t, which is the label. So y is the actual output. And that's kind of what I'm showing you over here. Okay, and so that's basically the error that has been produced by these neurons while processing this one input image. Okay, now and you know, when you're doing training, what you're essentially doing is you're trying to minimize a cost function, right? And so the cost function C is basically, you know, y1 minus t1 the whole square plus, you know, y2 minus t2 the whole square, and so on, right? And so basically differentiating the cost function by the value of y gives you y minus t, right? And that's kind of defined as the error, right? And you can see that it's basically the difference in each individual neuron output. So I'm defining that as the term DL, right? So this is basically the error. So error is D. And what I want to do is, you know, for all the neurons in this network, I want to figure out what is the error in that neuron, right? So basically, if its value were to change by a little bit, what effect would it have on my final cost function? Okay, and so this equation shows you, you know, once you know the error of this last stage, which is easy to compute based on the label, I want to back propagate that error and find out how wrong was this neuron, how wrong was this neuron, and then take it all the way back, right? Which means that if that neuron had changed by a little bit, what impact would that have on the cost function, right? And so, you know, this equation expresses that. It basically says that if I know the error of layer L plus 1, I know the error of all the neurons in layer L by just multiplying it by this weight matrix, right? And in fact, the transpose of that weight matrix, right? So you use a certain weight matrix WL plus 1 while doing the forward pass. For the backward pass, you're going to take the transpose of that matrix, multiply it by the error of these neurons to get the error of these neurons over here. Okay, and so there is a backward pass that looks exactly like the forward pass, which is simply taking the, you know, during the forward pass, you took the inputs and propagated all the way forward. In the backward pass, you're taking the error from this last stage over here because you know what the label is, and you're back propagating it with a matrix multiplication to figure out the error of each neuron in each layer. Okay, so the forward and backward passes look very similar. It's essentially the same kind of computation. Now, in addition to that, what you're really interested in is not the error of each individual neuron, but how much should each weight be adjusted so that the cost function is lowered, right? So ultimately what I want to do is to figure out how much should I nudge each neuron by, right? And that's basically this equation over here. It's basically saying that, you know, let's take a specific weight L. How does the cost function change if WL is changed by a little bit, right? And you can, you know, use the chain rule over here to come up with this equation over here, right? And so if I want to figure out how does this weight impact the final cost function, I can figure that out by taking the error of that neuron and multiply it by the activation that is produced by that particular neuron, right? So the output of that neuron multiplied by its error gives me a sense for how each weight should be adjusted. Okay, and so you know, so let me just kind of recap on this next slide over here, right? So in training, there is a forward pass that says I have the input image X. I'm going to multiply it with a series of matrices W in the forward pass to finally produce my output Y. Since I know the expected output, since I know the label for this input, I can now compute, right? So basically go through the label to figure out the error, which is dy. Now I go through a backward pass where I use dy and the transpose of those same weight matrices to compute the errors of each of the neurons in each and every single layer, right? So there is the backward pass where I essentially compute the neuron errors. And then there is a third step, which says now that I've computed the neuron errors, which is dx, I'm going to multiply it with the activations that I produced in the forward pass to compute the weight gradients, right? To compute the DWs that need to be applied to each individual weight, right? So there are essentially three steps. There's a forward pass, and during the forward pass, I'm going to save all the activations that I produced. Right, so all the activations which I'm calling X. Then I have a backward pass where given dy, I compute all the errors for each neuron. And then I take these errors dx, multiply it with the activations that I saved along the way to finally produce dw. Okay, so I was not planning on doing much more math than this, but let me see what questions you have and see if I can answer something simple enough to address these. Okay, so far nothing. So I hope the high level view of training is clear, right? So it's basically the inference step, being repeated for the backward pass, and then using the activation saved in the forward pass to compute the weight gradients. Okay, so it's a more time consuming process. The other huge difference with training is that it's usually done in mini batches. So it's not just one image at a time, but it's maybe 100 images at a time. And so I have to compute all those, the weight gradients from all of those 100 images, add them up, and then I update the weight. Then I move on to the next mini batch. Okay, so it's 100 different weight gradients that are aggregated before moving on to the next mini batch. Okay. All right, so now I'm going to go through some of the basic papers that have shown how to kind of tackle this additional burden being placed by training. We're going to start with the assumption that the training is happening on a GPU, right? So this is kind of the assumption made in the VDNN paper. Sorry. Right, so in that paper, they're basically saying, let's say that I have a single GPU and I'm doing the training process. And because the batch size is large and because convolutions produce these large feature maps, right? You have several output feature maps. They all have to be saved. And because the batch size may be 100, I have to do it for 100 such images, right? And so during the forward pass, you are saving a very large number of activations. That needs very high memory capacity, right? It easily exceeds the capacity of the on-chip caches. And in many cases, it can even exceed the memory capacity that the GPU has, right? And so at that time, the 12 GB, a GPU with 12 GB memory was kind of state of the art. And they basically showed that for many of these state-of-the-art neural networks, that 12 GB was not enough, right? And so, to deal with that constraint, you would have to do other things in the algorithm to make it work, right? And that was either costing time in terms of convergence, or it was costing you in terms of accuracy, right? And so they basically introduced this fairly simple technique, which said that when you exceed the memory capacity, right? So you have layer 1, layer 2, layer 3, and so on. Each one is producing these output feature maps, which have to be saved, right? So as you're making the forward pass, the stuff over here is not going to be touched for a really long time, right? And so this basically gets copied over the PCI bus into the CPU's memory, right? And then as you're doing the backward pass, when you're about to get to layer 3, that's when you copy this memory back from the CPU memory back into the GPU memory, right? So because this is such a deterministic process, you know when to offload data, you know when to prefetch it, and that's how you are basically making sure that you're not just constrained by the 12 GB of the GPU's memory, but you can also use the CPU's memory as an offload location. Okay, so fairly simple idea, but it kind of also shows you that this is that you can overcome the constraints, but there's all this data movement that is involved during training, right? And so that's kind of one of the big bottlenecks. And what I'm referring to over here is data movement within a single node. So that's kind of the key bottleneck that I'm going to be discussing with these few works that focus on training, right? So with training, the main bottleneck is the fact that I have to store these activations during my forward pass. I have to also compute all these weight gradients and update all the weights. That's another example of large data movement. And what we're trying to do is we're trying to kind of minimize all of this data movement. So the VDNN paper is essentially focusing on a single node and saying that in that single node, you have some GPU memory, you have some CPU memory. Sometimes you have to copy things back and forth, right? And it does not reduce the data movement, but it basically shows you how you can train large batches in spite of the GPU's memory capacity constraint. Okay, I'll soon also talk about data movement between nodes. That's the other major component in training. Okay, then there was also this paper which was from a wide group of institutions. And it was essentially a competing approach to what the VDNN paper had shown, right? And it essentially says that, while you're storing these activations, you have an opportunity to do some compression. And they identify, 3 different opportunities, and they say that, in 2 of them, the compression is lossless, and in the third approach, you can just basically choose to throw out some of the bits of your activations, right? And so, many works have shown that, during training, you do need higher precision. So when we discussed quantization and when we talked about low precision yesterday, we were focusing on inference, right? And when you're doing inference, you can get pretty good results even with 8-bit math. That is not the case with training, because in training, what you're doing is you're kind of aggregating these very small weight gradients. And so you do need higher precision of at least 16 bits and maybe even higher. And so this paper is essentially saying that, yes, you do need to do, 16-bit or 32-bit math, but the activations that you're producing during the forward pass, it could, you could potentially get away with just 8-bit precision. And, then they have experiments to show what effect that has on accuracy, right? And so it's one way of reducing the storage that you need during the forward pass. Okay, so, these are different ways of trying to reduce the storage requirements and the data movement during training. Okay, and then similarly, even the VDNN, the authors of the VDNN work also had a follow-up paper that basically said that, there's very high sparsity in these activations, and so doing some compression algorithms can reduce that requirement too. Okay, so now let me talk about multi-node training. Right, and so usually when you're doing training, it's this is an operation that lasts days and weeks. You're processing through millions of images, and you're doing many epochs of training, right? So you're essentially creating these mini batches. Once you've gone through all of your, let's say, million images in your training set, that's the end of one epoch. Then you do a second epoch, and you keep doing this till you have convergence, right? So this is an operation that takes many weeks and requires a large amount of compute. You can make things faster, of course, by using a large number of GPUs and a large number of TPUs, right? And so when you put many of these machines to work on your training task, there are different kinds of parallelism that you can exploit, right? So one approach is to do what is called data parallelism, which says that every GPU or every TPU has the entire deep network model, but each GPU is going to handle a different image, right? So if you have 16 GPUs working on this, each GPU is going to work on a different image. And so you're working on 16 images in parallel, right? So the forward pass, the backward pass, all of that is kind of being done independently on each GPU. And there are no dependencies between these GPUs at that point. But before you can move on to the next mini batch, you have to aggregate the gradients that have been produced by each one of these GPUs, right? So in this case, there's no exchange of information while you're doing the forward and the backward passes, but you do have to exchange the gradients once the mini batch has completed. Okay, so that's an example of data parallelism. And it works better for convolutions because convolutions have fewer weights, and so there are fewer gradients that you have to exchange. The second kind of parallelism is model parallelism, which says that I'm basically going to have so the model is distributed across multiple GPUs, right? So each GPU is going to handle a subset of the model, and it's going to handle a subset of all of the neurons, right? And so essentially, one image has to be sent to all of the GPUs, right? So all of the GPUs are going to see parts of each image, right? And so what ends up getting exchanged are the feature maps for all of these images, right? So the gradients, not so much, because each GPU is responsible for all the operations that pertain to one weight, right? And so those weight updates are local, but the feature maps have to be seen by all of the GPUs. Okay, and so this is a better fit for fully connected layers. And there was a paper a couple of years back called HiPEAC, which was essentially using a hybrid of data parallelism and model parallelism to train one deep network, right? So you can have hybrids of these two approaches as well. Okay, so if you take, so data parallelism has clearly turned out to be more common. And it's also what is used in what is called federated learning, where you have this distributed network, many phones all doing their own stuff. But for privacy reasons, you can't take the information on the phone and send it to the data center, right? And so if you're trying to do training on the data on the phones, then you basically have to do the training locally, and then you have to send the weight gradients to the data center, right? And so data parallelism is kind of more common even in that context. Okay, so if you're starting with the baseline that has data parallelism, what you're concerned about is the exchange of these gradients. And so there's been some work that shows how the gradients can also be compressed. So there was this work that came out of a group at Stanford, which showed that as all the weight gradients are updated, if the change to one of the weights is not very high, you can keep that change locally, right? So you're not throwing away that information, but you're basically saying that the next mini batch does not have to see a gradient change that is not above a certain threshold. So only when the local gradient exceeds a certain threshold does it get propagated to all the nodes, and all the nodes then update their weights, right? And so it's kind of partially lossy, right? So you're never throwing away a weight gradient, but you're basically kind of being lazy about when that gets propagated. And they've basically shown orders of magnitude reduction in the gradient data that has to be exchanged. Okay, let's see if there are any questions from anyone. There are a couple of questions which I think pertain to the previous things that we were discussing. So I'll get back to that later. Or maybe in the break, which I'm kind of overdue for. But maybe I'll kind of finish training before I take that break. We're almost at the end. Okay, so now let me kind of move on to a couple of other topics in terms of training. And this is pertaining to what commercial systems are trying to do, right? So we saw that the Google TPU v1 was focused on inference. The version 2 focuses on training. And you'll see that there aren't that many differences, right? So one is that it goes from 8-bit integers to 16-bit floating point. It uses what is called bfloat16, which is a fancy term for just saying it's like IEEE 754 32-bit floating point, but I'm just going to drop the last 16 bits of the mantissa. So it's just using a 7-bit mantissa instead of the 23-bit mantissa. And so because you're doing floating point, because each systolic element has a more complicated ALU, it takes up more area, right? So instead of having a 256 by 256 grid, which is what V1 had, you'll see now that they have two 128 by 128 cores, right? And so that essentially halves their peak throughput from 92 teraops to 45 teraops, right? So it almost seems like it's a more inferior design, but it's not. This is a much better design, more area, much better memory interface. It's using HBM for high bandwidth memory. But because each ALU is doing a different operation, it seems like it's got lower throughput. Okay, but in most regards, this is a better chip than the V1. The other key contribution over here is they basically say that training is a distributed process. They're going to use a bunch of these TPU V2s to work on one training task, right? And so they have 64 or 256 of these TPUs that are connected with a 2D torus. And because there is such frequent communication between these chips, they essentially have, they essentially have the interconnect framework that is inside the chip itself, and that occupies about 13% of the chip area, right? So this is not offloaded to an external memory interface. They have a custom interconnect that is implemented on each chip, basically going out to the north, south, east, west neighbors, and has a very high bandwidth as well. Okay, so that's what the TPU V2 does. There are other examples of these training chips. There are examples from GraphCore, Cerebras. Some of the innovations in both of these chips is that they actually don't have any external DRAM, right? And so the TPU is essentially saying that I'm producing all these activations in the forward pass. That's stored in the 16 GB HBM, right? The 16 GB per chip, and it can be accessed at very high bandwidth. And so Cerebras and GraphCore are both saying that, I'm just going to have lots of these chips. Each of these chips is going to have lots of SRAM. All that SRAM put together is going to give me several gigabytes worth of memory. So in the case of Cerebras, I think, all of their chips put together give you an SRAM storage capacity of 18 GB, right? It's not a whole lot, but it's good enough for most modern training workloads, right? And it's basically saying that, by just putting it in SRAM, I'm completely avoiding having to go to external DRAM. GraphCore also introduces this concept of saying that, if you do run out of this SRAM space, you can just throw away some of the forward pass activations and you can recompute the data when you're making your backward pass, right? So it's essentially saying that data movement is so expensive that I'm actually willing to do more compute to avoid the cost of storing the data and fetching it from memory. Okay, so both of these works are essentially again putting together a large number of chips to do distributed training, and these two in particular are even kind of eschewing external DRAM and saying that the on-chip SRAM is so abundant that I can store my my forward pass feature maps in that SRAM. The other key innovation with Cerebras is it uses what is called wafer scale integration. Right, so they essentially, once you've created an entire wafer of chips, they're not actually breaking it up. They're essentially using metal layers to implement the communication between those chips, and they're kind of keeping that wafer intact. Right, so all kinds of engineering issues with that, but that's kind of their main investment, and that's their key innovation to say that I'm just going to give you an entire wafer because you're anyway going to have to buy a bunch of these chips to do distributed training. And so by keeping the wafer intact, I can have extremely high bandwidth communication between these chips, right? But now they have to deal with cooling, power delivery. They have to deal with the fact that there'll be errors on some of these chips, right? So there are all these engineering issues which they've not fully explained how they address. But I think that's the stuff that they will kind of that they'll figure out over the next few years. Okay, so I had one more discussion on scale deep, and I don't think I should get into this. This I've taken more time than I was initially planning, and I want to save some time for spiking neural networks. So maybe I'll do the 5-minute break right here, see if you have questions, and then I'll, maybe at 9:22 or whatever, 22 minutes past the hour, I will start discussing spiking neural networks. Okay, so let me just pause here for 5 minutes and see if there are some questions, and then we'll move on to the next topic. Yeah, so there's this question about, is the trend towards bfloat 16? So yes, right. So for the longest time, training was always done on 32-bit floating point, and people said that it's really hard to get away with anything less than that. Then a few years back, there was a shift to say that 16-bit floating point is possible, but not by using the IEEE 754 16-bit format. It has to be done with something like bfloat 16, right? Which essentially says that I still want the same 8 bits for the exponent, but I'm willing to throw away some of the mantissa bits, right? So with this new format, they showed that 16-bit floating point is also good enough for training. There are some other formats also in the mix. So I know that folks at Intel had a paper on something called FlexPoint, where they're kind of looking for locality in the data and kind of changing the number of bits used for exponent and for the mantissa. So there are a few different formats, but I think the general consensus is that 16 bits should be enough. Yeah, and so most accelerators for both inference and for training are kind of gravitating towards 16 bits. Inference accelerators can also do 8 bits, and so even the accelerator from Grok, I think, does 8-bit integer arithmetic. But for training, some format using 16 bits is popular. bfloat 16 and FlexPoint have received the most attention so far. So hopefully that answers your question. Another related question is about using bfloat 16 in the TPU, but using FP32 accumulation. So I did not know of that. So I did not know that they may be using more bits for the accumulator, and it certainly seems plausible. like at least in inference, right? When we talk about the operations being done in 8 bits, the accumulator still uses 24 bits and then finally truncates the result to 8 bits, right? So this is kind of done even in inference. So I wouldn't be surprised if they have more bits for the accumulation, and then some of those bits get thrown away when you're producing the final result. So I don't know much about it, but there is a paper about the TPU v2 in CACM. I think it just appeared in the July 2020 edition. So if you look there, I'm sure it might have this detail about whether they have more bits for accumulation. Yes, and some of you are commenting on the NVIDIA chips also having lower precision, and that is correct, right? And so yeah, the newer NVIDIA chips have support for this, as well as for things like sparsity. Yeah. So this is an interesting question. So can you take an 8-bit chip and maybe use software to do 16-bit training? And I'm not sure if that's doable. Yeah, so because of the mantissa exponent, the implicit one, all of that, it just seems like it might be a little too complicated to handle. So I've not seen any work that does it. I'd mentioned earlier that you can actually apply to get some credits on the Google TPU cloud, and you can use it for your purposes. I'm not, I'm sure you have an option where you can ask for V1 chips, and I'm not sure how the programming process, how you may have access to change the programming process and be able to do training. So I don't know the answer to this question. It's an interesting issue. Maybe call me skeptical. I just feel that the overheads might be so high that it's not worth doing. But it's an interesting question to ask for sure. Okay, so there was a couple of questions earlier that I didn't quite get to. Are there any machine learning approaches which would benefit from the analog approach, right? And so are you essentially saying that analog may improve the accuracy because it inherently has some noise in it? And that, so I don't know if I'm interpreting your question correctly, but if I am, then I think it is possible, and I don't think people have looked at this. So what you're essentially saying is that in a lot of machine learning training techniques, I artificially inject noise, right? So things like dropout are purposely injecting noise because you want to avoid overfitting. And so if I'm operating in the analog domain, is that automatically injecting noise and I don't have to do anything explicit? So it's a reasonable question to ask, and I don't know if it has merit. I should also point out that the analog approach that we saw earlier, it can be very effective for inference, but it's harder to exploit for training. And the main reason is that when you're doing training, you also want to nudge the weights as you go along, right? So what that means is that after every mini batch, you want to reprogram the weights, and the reprogramming of the weights is a very expensive process, and you can only do it one cell at a time. So if you have a 128 by 128 crossbar, it's going to take 2 to the 14 steps to program each cell individually, and each cell itself can take many hundreds of nanoseconds. And so using analog for training in general is not a great idea. There are people that have made assumptions about better cells and have shown that it's possible. But we may not see those cells in a commercial setting for a really long time. Okay, so I digress from your original question, but hopefully that gives you a little bit of insight. What happens if the error is injected in a layer at the middle? So I'm not sure what that's referring to, right? So usually the error, so if you're referring to the error during training, right? So usually you start by knowing the label at the very last layer. So it's only those labels that are known. And so usually the error kind of starts at the last layer and then kind of propagates all the way to the front. So I'm not sure if you can inject error in the middle, right? Now, if you're talking about the analog accelerators and error in the middle, I'm not, I mean, the error correction method that I explained is something that can apply to any of the layers. So that should also be orthogonal to the layer that the error is injected in. So, so if I'm misunderstanding your question, do add a little bit more detail and I can try to answer it later. Can any of these solutions use fixed point instead of float, right? And so I think people have tried that and failed. So, one of the reasons is that there is a wide range in the values being produced during training. And because of that range, fixed point is less of a fit, right? Because in fixed point, all the values are being divided by the same denominator, whereas float allows you to have an 8-bit exponent, and so it can have a much bigger range in terms of the values. And so for that reason, I think fixed point efforts have not quite succeeded. Yeah, but this kind of relates to to that earlier question about, can I hack into the TPU v1 and somehow make it run a training task? I think this is one of the many challenges that you would have to overcome in doing that. What about approximate logarithmic numbers? And I think this does have merit, right? So there was a blog post recently in the Computer Architecture Today blog, which talks about the posit number system. And it essentially says that, floating point has been around for a really long time, and we are kind of forcibly using it to do deep network training. Now that we better understand the needs of deep network numerics, can we come up with a different numeric format, right? And so I don't know much about approximate logarithmic numbers, but I think this is a good time to explore some of these alternative number systems. And so I think the blog post on the Segoch blog, I think that may be a good place to start, right? And it talks about how the posit number system may be a good fit. So you can use that as a starting point. So does the analog computing system have a scaling problem? And yes, it does, right? And that's kind of why we worked so hard to kind of distribute the computation in time and space so that the value does not explode and go past the range of the ADC, right? So we said that, I'm implementing an 8-bit ADC. Because of that, the contribution from each cell can only be so much. I can have only so many rows in each crossbar, right? So I was very careful to not exceed this analog range. And so it does have that scaling problem, and that's why we kind of have to be very careful in that design. So one approach is to just blow past the analog range and just drop the last, hopefully drop the least significant bits, and that way it's less of an engineering problem. But at least in the early works, people have tried to kind of stick to those constraints so they're not dropping any bits. Yeah. Any FPGA approaches that you know of to enable training? So I think some of the brainwave and catapult efforts, like I can't remember if it was inference only. I kind of feel it was also for training. So again, I'm not, this is not a space that I track super closely, but I would start with the brainwave and catapult projects at Microsoft, and they probably have some information out there about training workloads too. Okay, so I think let's move on to the last topic, right? So I think I have only half an hour left. I was hoping for a little bit more time, but even beyond the 2-hour time slot, I'll stick around for 20 minutes and answer any questions. So let's move on to the last topic, which is spiking neural networks, right? And so now we are going away from, I'm skipping all of these slides on scale deep, and you're welcome to look at it later. But now I'm kind of moving into things that are closer to biology. But I'm still going to stick in the hardware space, right? But we're essentially saying that until now, we were using what are called artificial neural networks, where the initial inspiration was from biology, right? So the neuron was designed to emulate, what people thought were the mechanics in the brain. But the training process very quickly deviated from the training process that's used in biology, right? And so the training process uses stochastic gradient descent, which is a very mathematical process, right? It's essentially saying that I have a certain cost function. I know the labels. I'm going to keep, adding to the cost function, and I'm going to keep nudging the weight so that the cost function keeps reducing, right? So it's using, differentiation and all of these operators which are not used in biology, right? And so, there are certain groups that are still holding out hope that if we kind of stick to if we stick to biological operations, maybe we'll end up with a system that consumes very little energy, right? So our brain consumes about 20 watts of power, right? And so maybe we'll end up with something that consumes a lot less energy and is also very accurate, right? I mean, we still kind of trust our brain to do many of these cognitive tasks over an AI, right? So the hope is that we'll get better accuracy and more energy efficiency by sticking to processes that are as brain-like as possible. Okay, and so again, I won't go into the details of this biological stuff. I have some more information over here that talks about the biological aspects, but it's kind of it's a little dry for me to walk through this list of numbers. So I'll just leave it here for reference in the slides. But let's move on and essentially kind of define what our neuron model is going to be. So before I do that, right, here's my general take on this approach, right? And so yes, the brain is awesome and we should emulate it as far as possible. But in some sense, right, the brain uses these electrochemical operations, right? In some sense, it's kind of limited by that. And in some sense, it has this low energy because it's using these electrochemical operations, right? And, we are designing most of our chips using a different process, right? So we can't expect to have the same energy efficiency that these electrochemical processes have, right? And so, there are some things that the brain does where it is constrained by the fact that it is using this electrochemistry, right? And so, trying to emulate those processes, in silicon does not always make a lot of sense, right? So we have to kind of be careful about, what parts of the biological process we actually borrow and which ones we stay away from. Okay, so this is just kind of a bit of a warning signal saying that, while it's nice to have the brain as something that's worth emulating, let's not just blindly emulate every single thing that the brain does, right? In some sense, you can say that the training process for the brain is really slow because, it's not until, 5 years of age that I learned to read something, right? And so, one could argue that the training process used by the brain is actually really slow. And maybe I'm better off relying on something that is mathematical and that uses stochastic gradient descent. Maybe that is the fastest way to learn, right? And so, that's just a warning to kind of keep at the back of our heads at all times, right? But, while we are diving into spiking neural networks, let's just say that it's good to emulate some of the brain processes. Let's see what is the best we can do in terms of algorithms and in terms of hardware. Okay, so here's kind of what the neuron model assumes. It's what is commonly referred to as the leaky, integrate, and fire model, right? Which essentially says that, sorry, my handwriting today is even worse than usual, right? So every neuron basically has a certain potential and it receives inputs in the form of spikes, right? So if it receives an input, if it receives an input spike on input number 1, because of the weight associated with that input, the potential goes up by a certain amount. In the next time step, you may get an input on input 2, right? So there's a spike on input 2. Because of a different weight associated with that input, the potential rises by a different amount, right? Then you get an input on input 3. That may have a negative weight, so the potential may actually reduce, right? So over time, as you get these spikes as inputs, the potential kind of goes up, goes down, right? And when it finally reaches a certain threshold, at that point, we say that we've seen enough inputs, we have now acquired enough potential that I'm going to produce an output spike. So at this point, the neuron produces an output spike and its potential kind of goes all the way back down to this resting potential. Okay, so this is basically the operations in the brain, and we are essentially saying that, instead of getting all the inputs at a single time and doing the dot product, let's use this process where the inputs arrive in the form of spikes over time. And every input spike basically does an addition, right? There's no multiplication happening now, right? The potential basically goes up or down based on that input spike. And when it finally reaches a threshold, it produces a spike that then moves on to the next layer. right? And then my potential comes all the way down, and then the process repeats again. Okay, so this is kind of the basic neuron model that we're trying to implement. There's another feature over here that says that as time passes, if you don't receive any inputs, what I showed over here is that the potential is kind of flat. Okay, that's not the assumption being made in state-of-the-art neurons, which says that, in biology, the ionic potential of a neuron does not kind of stay the same. Over time, if it does not receive any inputs, these ions basically dissipate into the plasma around the neuron. And so its potential actually starts to drop, right? So the realistic curve is, yes, your potential goes up, but then it starts to kind of leak away. Then you get the next input spike, your potential goes up, then it starts to leak away, then you get the next input and so on, right? So it looks kind of closer to what I've shown over here, where every input spike increases the potential, but then while you don't receive spikes, the potential starts to leak away exponentially. Okay, so that's why this is called a leaky integrate and fire, right? So each input spike is kind of adding or integrating your potential. And then when you reach a threshold, you fire. And if you're not getting inputs, your potential starts to leak away. Okay, so any questions about this? Okay, looks like maybe this is more basic than you were expecting. So this is perhaps well known to many of you. All right, so now let's move into how information is encoded in these networks. And so there are two main forms of encoding, and there are others as well which have not got a whole lot of traction, but the two most common ones are rate coding and temporal coding. In rate coding, you're essentially saying that when I give you an input, I get a certain amount of time to provide that input, right? So let's say that I get 16 cycles. And I'm instead of using milliseconds, I'm using a hardware term, right? So I'm basically saying that I have 16 cycles to provide my input. If the input is, let's say, red, right? And red maybe corresponds to a pixel value of 23, right? It does not, but I'm just making up these numbers right here. And then you have a separate input which is blue, and that corresponds to a pixel value of 95. Right, so I want to convey these numbers as input, and so basically red is conveyed as 2 spikes that show up in these 16 cycles, right? So the rate of spikes is conveying the value. So red is conveyed as 2 spikes, but blue, which is almost 4 times as much, may correspond to 8 spikes during the 16 cycle window, right? And so that's essentially how I'm conveying the values of these input numbers by the number of spikes that are propagated during the 16 cycle window. So that's what a rate coding refers to. A temporal coding says that I'm going to convey these values in terms of time. So again, if I have a 16 cycle window, a value of 23 is conveyed as an early spike. So a single spike that shows up at roughly time 23. Whereas a blue value of 95 may show up as a spike that comes much later in that window, right? So you have a single spike that comes much later, right? So this represents red, this represents blue. Okay, so that's what a temporal code is. And you'll see over here that that clearly a temporal code seems like it would be more energy efficient, right? I'm using a single spike to convey that information, and I'm using that single spike at a specific time to encode that information. So it may also give me a different a different neuron model than the artificial neuron model that I'm used to. Okay, and I'm going to talk a little bit more about that particular aspect. Okay, so now let's kind of look at a rate-coded neuron, and as if I were to come up with an equation for the potential of this neuron, right? So each time I get an input over here, the potential goes up by W1. Right? And so if I see F1 spikes over here, the potential has basically gone up by W1 times F1. At the same time, I'm also getting inputs on this second input that has weight 2, right? And so the potential, the overall potential increment is basically the number of spikes I see times the corresponding weight for that input. And you'll see that this equation is a lot like the dot product equation that you see in artificial neural networks. Right, so in some sense, the rate coding is nothing but an emulation of an ANN. So in some sense, I can take a rate-coded spiking neural network and I can configure it so that it behaves exactly like an artificial neural network, right? And so we're essentially saying that this is a spiking neural network that has the same power as an artificial neural network, right? So if I can come up with an ANN that gives me an accuracy of 95%, I can also create a rate-coded SNN that gives me pretty much the same accuracy, right? And there are a few approximations that I'm making over here, but to the first order, this is roughly true, that I can configure an SNN to behave, or I can configure a rate-coded SNN to have the same behavior as an ANN. Okay, and it turns out that such a design is likely to not be super efficient, because what we are doing in this case is we are saying that if it's a value of 23 that I'm trying to pass on, I'm doing this by producing 23 different spikes, right? And each of those spikes is basically doing an increment of the potential by W1, right? And so I'm basically doing 23 additions to capture this input value of 23. Right? Whereas if you look at an artificial neural network, this value 23 is encoded as a 5-bit number, right? And then it performs a certain multiplication, right? And so it's basically relying on a 5-bit multiplier in an ANN, right? And so because of this logarithmic transformation, maybe the multiplication is more efficient, right? So multiplication on log of a certain bits is maybe more efficient than doing addition on a linear number of those of that information value, right? And so that's kind of what I'm trying to convey here, right? So here's a value 23 corresponds to a linear number of additions in an SNN, but corresponds to a multiplication that is a function of the logarithmic of 23. Right? So it's not clear that a rate-coded SNN is necessarily the best implementation. It's a good way of kind of cheating and getting the same accuracy as an ANN, but it's not necessarily a better design. Okay, so I hope that's clear, and feel free to ask questions if you have them. So normally temporal codes are inversely proportional to time to spike and not vice versa, and that is correct, right? And I think my example was not the best design one, yeah. How about rate coding with valued spikes instead of binary spikes, right? And so, again, this seems like, it's not clear that that's going to be better than an artificial neural network, right? So we're essentially saying that, so at this point we are, there are two things to consider, right? So firstly, are you creating something that has more power algorithmically? And the second thing is, are you creating something that's more efficient in terms of hardware, right? And so this proposal of taking rate coding and attaching a value with every spike, I think that's certainly more energy efficient, right? Because it prevents me from doing these 23 separate additions. But algorithmically, it's going to have the same power as rate coding. And in terms of hardware efficiency, I would argue that this is sounding a lot like an artificial neural network itself. So in some sense, I'm kind of taking the position here that rate coding SNNs are really not giving you any additional power over an artificial neural network, and they're also not giving you any efficiency advantage over an artificial neural network. Okay, and again, this is I think this is a problem that a lot of smart people need to look at, and I think this thinking will evolve over time. But I'm kind of sharing what my current thought process is, and we can have a deeper discussion after I'm done with a few more slides. Yeah. Okay, so as I said, the position I'm taking over here is that maybe instead of focusing on rate codes, we need to focus on temporal codes. And the reason for that, of course, is firstly that I'm providing a lot fewer spikes, and as I'll show you soon, an architecture that uses a spiking neural network is going to have high efficiency only if it's a very sparse set of inputs, right? The number of spikes has to be relatively small. That's what minimizes the number of accesses to large buffers and so on. And so the efficiency is a strong function of the sparsity of the spike train. And so for that reason, I think temporal codes is kind of where we should focus on, because every input value is encoded as a single spike at a specific time. The second reason why I think temporal codes, have some potential is because it leads to a slightly different neuron model, right? So, the traditional artificial neuron is essentially doing a dot product. It's basically a weighted sum of inputs and then seeing, how high that sum is. Whereas if you look at temporal codes, what they're really looking for are clusters of inputs. So, if I have one input that comes here and one input that comes after a large amount of time, what it means is that the potential kind of goes up over here, then it starts to leak away. And then when I get this next spike, it goes up again, right? But maybe this potential is not high enough to exceed the threshold. Whereas if I had those same inputs kind of back to back, my potential goes up at the first one. It doesn't have time to leak too much. Then I get the next input that takes up my potential high enough. And maybe this exceeds the threshold, right? So the threshold was not exceeded over here, but it is exceeded in the second case, right? So the timing of the spikes and the leak that happens between those spikes kind of determines if this neuron is going to spike or not, right? So in some sense, this is a neuron that is more of a cluster detector than it is a weighted sum detector, which is what an artificial neuron is, right? So in some sense, it has a different description, and and correspondingly, it maybe has a different kind of power, and maybe it has more power than a traditional neuron that we know of. So that's another reason why I think temporal codes are exciting. It's an area that has not seen much work, right? So clearly, if you look at the machine learning community, they're all focusing on artificial neural networks. It took 50 years, and then finally we made the big breakthroughs that have then resulted in these large improvements in the last 10, 15 years. We have not seen any of that for temporal codes for spiking neural networks, right? So this is an area that's, I think, kind of screaming for attention. And my hope is that, given that this neuron has a different property, maybe there's more science to be uncovered over here. Maybe we can come up with training algorithms that give us really high accuracy when the neuron operates as a cluster detector as opposed to a weighted sum detector. Okay, any comments, any questions about this? Right, again, like I said, this is an area that's not very heavily studied. I'm not a spiking neural network algorithm designer, right? And so in some sense, I'm sharing what I have read so far and kind of what I have concluded from that so far. Okay, but I see temporal codes as being where the action is. With 10 years of focused effort, maybe this is where we'll see the next big breakthroughs. And in terms of hardware efficiency, it also seems to be more favorable because it leads to much higher sparsity as well. Yeah, so are there any hardware accelerator implementations? And that's what's coming up next. So I'm going to talk about one example design from my group that is able to beat artificial neural network accelerators as well. Okay, so yeah, so let's kind of move on, right? So let's talk a little bit about training. So we'll still stay in the algorithmic space before we dive into the hardware aspects. So how are these spiking neural networks trained, right? So one approach, which is very effective when you're using rate coding, is to say, let's just stick to supervised learning like we do with artificial neural networks. Let's have a cost function. Let's use backpropagation, stochastic gradient descent to nudge the weights so the cost function is minimized, right? So we're going to, so moving away from biology, using math to figure out, what are the weights that give me the lowest cost function, right? So people, and that's kind of been that's been the popular approach so far. And it works very well for rate-coded SNNs because, like I said, rate-coded SNNs are nothing but an incarnation of an artificial neural network, right? And so, you can use backpropagation, you can figure out the weights for an ANN, and then you can use the same weights for a rate-coded SNN as well, right? And so, most of the success stories for SNNs have kind of been with this approach, which in my view is a little bit of it's a bit of a shortcut in my sense, right? It's, if you can establish an equivalence, it should not be a surprise that a rate-coded SNN was able to behave exactly like an artificial neural network. Okay, so that's kind of been the popular approach. But the more biologically, plausible approach is what is known as STDP, the fancy term spike timing dependent plasticity. What it essentially is saying is that every neuron has its own localized training process. Okay, so here's a neuron, and you have all these inputs over here. Let's say they have some weight at some point of time. Okay, now let's say that a spike showed up over here, and that spike led to an output spike, right? And so that spike and the potential increase because of that spike were enough to trigger an output spike. What that tells this neuron is that that input spike was super important, right? That's kind of what helped me kind of get over the threshold. And so it means that whatever input I receive or whatever spike I receive on that input, that seems to be an important input, and its weight should be increased. Okay, so if an input spike leads to an output spike, that is a signal to this neuron that maybe this weight W1 is important, and I need to increase it by delta. Okay, so it's a very localized training process, right? I don't have to see the final result, and I don't need that final error or that final gradient to backpropagate all the way to me, right? I don't have to see what any of the neurons are doing. I don't even have to see the final result. All I'm seeing is, what did I do as a result of this input? And if I produce an output spike, then, let me nudge my weight a little bit, right? So you can see that this is a very efficient process because it does not require any communication with anybody else, right? Every neuron is kind of training itself based on its own inputs and based on its own output. Similarly, if I produce an output spike and then sometime later an input shows up over here, what that means is that that input is not very relevant and not very important. In fact, it had no role at all in this output spike that I just produced. So that's a sign that this weight W3 needs to be decremented by delta. Okay, so if I were to express this as a graph, this is what STDP looks like, right? Where the y-axis is the delta W, right? So how do I change my weight? And the y-axis is the x-axis is the spike arrival time relative to the output spike, right? So when the spike arrival time is negative, it means that the input spike arrived just before the output spike. That basically says that this is an important input and the weight should be increased. And the closer that the spike arrives to the output spike, the more I increment the weight, right? So it's really important if this is the input spike that led to the output spike. Whereas if the input spike came after the output spike, that's the positive x-axis, then the weight needs to actually be decremented. And again, the inter-arrival time is what determines the shift in the weight. Okay, so this is actually a biological process used in neurons in our brains, and of course it's been deployed in spiking neural networks, and it turns out that it has lower accuracy than the mathematical artificial neural network approach, right? So SNNs that use STDP to train themselves usually give you lower accuracy than the mathematical approach, right? And that's one of the reasons why spiking neural networks have not taken over the world, right? If you try to be biologically faithful, it turns out that the results are not the best, right? And then the only way to kind of match the ANNs is to either use rate coding, which as I said, is a little bit of a shortcut, or if you use supervised learning and stochastic gradient descent, that's how you can match an ANN. But yeah, those are not quite biologically faithful approaches. Okay, so hopefully this training process is clear, right? So if you want to be biological, you can achieve training with very low overheads, but algorithmically this seems to be less compelling than the more mathematically intensive approach. So question about what are the initial values of weights in an SNN, and you're right that 0 would not give you any initial spikes, and so I believe they are just random. And again, I believe that that's probably what has also been observed in biology, but I've not read that literature as carefully, so I can't confirm that. Okay, all right. So now let's now see. So I've kind of been talking about the algorithms of spiking networks and what the trade-offs are, what these different models are. And so the question is, are spiking networks at all useful today, right? So in some sense, I've basically said that if you try to be biologically faithful, you're not going to get the same accuracy, right? And so why would anyone even use a spiking neural network, right? And so in some sense, today we are working a little hard to make a case for where an SNN may be useful. The hope is, like I said, in 10 years, people will come up with better algorithms for temporally coded SNNs, and that may exceed the accuracy that you get with an artificial neural network, right? And so, we need more investment in TSNN training algorithms. There was a paper from Google that appeared last year, which I think did a pretty good job. It took a huge jump forward, where it showed some simple models where the SNN can do better than the ANN. But these are relatively small neural networks, right? So I think we need a lot more effort there, so we can beat, state-of-the-art ResNet or EfficientNet or whatever, right? So that's a space that needs a lot more effort. So the other places where an SNN can be useful today is one where you don't have access to labeled data sets, right? So stochastic gradient descent is great when you know the labels for the data set and you can kind of do the backpropagation. But if you don't know these labels, then using something like STDP may be more beneficial, right? I mean, that's actually practical where I don't need a label. Every neuron is kind of training itself, right? And so that's an example where STDP and SNNs may make a lot of sense. It may also be useful where you kind of have to learn on the fly, right? And so let's say that you have these edge devices that are performing inference, and suddenly those edge devices are being faced with a different situation. Let's say that it starts raining, and so now you're seeing images that you have not been trained to see, right? Or you're seeing like a new terrain, maybe after an earthquake that you have not been kind of trained on, right? And so if you have to do some real-time learning on an edge device, that learning has to firstly be energy efficient, where STDP might be a good fit, right? Where you don't have the energy to do mini batches and stochastic gradient descent, right? So that's an example where real-time learning might make sense. It also makes sense because you don't have access to labeled data sets, right? And so being able to nudge the weights of a neuron based on STDP might be valuable, right? So again, I don't think people have shown good case studies of these usage scenarios. So I think this is a good area where I think more work can have very high impact. But that's an example where a spiking neural network can be shown to be useful today itself. Okay, another example is to use STDP to establish initial weights, right? It's basically saying that early on the weights are way off, right? And I don't need to do stochastic gradient descent over several epochs to figure out what those initial weights should be. Maybe I use something like STDP, which consumes a lot less energy, gets me to a good initial point, and then from that point on, I can use the more resource intensive SGD to nudge the weights further and make them even better, right? So basically, doing a quick and dirty training with STDP, and then doing a more precise training using stochastic gradient descent. So that could be another example where you use spiking for a while, and then kind of change to artificial neural networks later. Okay, so these are potential use cases. So there's this question about how does a neuron know that's a good thing that it produces a spike at a particular point in time, right? And so it does not, and so it may take a large amount of training over several inputs to kind of realize that some early decisions were actually incorrect. But this is kind of the basis of STDP. It's basically saying that I've seen enough inputs to produce an output, and I'm going to become really good at producing the same result when I see a similar input, right? That's kind of the basis of STDP. It's basically saying that, I'm not trying to classify something as a cat or a dog. It's just saying that when I see something that looks like a cat, I want this neuron to fire, right? And so when I gave you those inputs, initially you had random weights and you produce a spike. And so what I'm doing now is I'm kind of adjusting the weights to say that when I see that same set of inputs again, I want to continue to produce a spike again. Right? So that's how a neuron knows that that when it produces a spike, it was a good thing, because it's basically saying that I'm gradually training myself to always produce a spike when I see something that looks like a cat. Right? The initial spike may have been just random, but over time you get better at being consistent in producing those spikes. Right? So hopefully that kind of answered why STDP is the way it is. Okay, so I think I have just a few minutes. Well, I'm kind of at the 2-hour mark, but I'll spend a couple of minutes just discussing some of the hardware features, right? And so this table kind of gives you a comparison of ANN and SNN accuracy. You'll see that most studies look at rate-coded SNNs, right? So they're all kind of RSNNs. And with RSNNs, you can come relatively close to a state-of-the-art ANN. The TSNNs have seen less effort, right? So this is the Google paper that I mentioned. And so this is from an ISCA 20 paper that is from my group. And so, a TSNN does pretty good, but it's still, behind, it's still behind the state-of-the-art ANNs. Okay, so it kind of tells you that there's more work that needs to happen over here. I'm not going to spend much time on TrueNorth, but this was kind of the first commercial implementation that tried to do SNNs. Since then, we've also seen Intel's Loihi chip, right? And TrueNorth, it received a lot of press. I think it was, quite a breakthrough effort for its time, and it was certainly an ambitious effort. But if you look at some of the modern artificial neural network accelerators, they get much higher throughput than IBM's TrueNorth. And so now when you look back at IBM's TrueNorth, you can find a number of things that they could have done better, but clearly revolutionary for its time. And because I think we can do much better now, I won't spend a lot of time in this discussion today, right? So let's just kind of move on to the next piece, right? So why is hardware for SNN more difficult, right? So one of the reasons is the temporal aspect. So the input is arriving over many ticks, right? So over 16 cycles, I'm getting my input. And over that time, I have to retain my neuron potential, right? And so it's this temporal aspect that, that adds one more element to that for loop, right? So I had that earlier nested for loop that said, this is everything that a convolutional neural network has to do. Now, I have to also do it for time steps, 1 to 16. And so that adds one more dimension to the data flow. And because of that, it complicates the reuse of it more, right? And so that's why we have to come up with better data flows in order to do this. And so if you just take a baseline ANN accelerator like Iris, and you just convert it into a naive spiking implementation, it actually gives you a much higher overhead. And it's mostly because of this temporal component, right? So you'll see over here that relative to Iris, the energy per inference is much higher. It's kind of 30x less efficient. The efficiency comes down to the same level as Iris when we change things on the x-axis, right? And so what I'm changing over here is the bit precision, right? So this is basically 2-bit arithmetic. It's basically saying that if I use 2-bit weights, then yes, I can beat an artificial neural network that uses 8-bit weights. Right? So clearly not an apples to apples comparison. The other dimension over here is the sparsity level in the spikes. So this is saying that only 2%, this is 98, which means only 2% of all the spikes are actually, or 2% of all the cycles actually have spikes in them. So if the sparsity level is really low, then I can match the efficiency of an artificial neural network. Right? But if I go to a sparsity level of 40% or 40% of cycles have spikes, then the energy consumption is a lot higher, right? So the only way that an SNN can match an ANN is by exploiting high sparsity or by using low resolution weights. Okay, now starting with this naive baseline, you can improve on that further, right? And so that was the contribution in our ISCA paper that was presented last month, which basically said that I can change the data flow, right? And so I won't again go into the details because I'm kind of running out of time. But this kind of gives you the overview of the key contributions there. So it uses an output stationary data flow, which means that instead of storing the neuron potential elsewhere, once we bring the neuron potential into a register, let's keep it there and let's do all the computations for that input interval. And that reduces the challenge with managing the neuron potential across several time steps. It also shows how you can kind of compress the inputs. It also shows how you can exploit parallelism by working on several output feature maps in parallel, right? So with all of these, with this new data flow added in, you can actually do as well as Iris, right? So the crossover point is a little bit better. So if you assume a sparsity level of 90%, a 4-bit spinal flow, which is this new architecture, is about 5x better than an 8-bit Iris. If you try to do an apples to apples comparison, if you assume a 4-bit iris, then at 90% sparsity levels, the new design is about 1.8x better, right? So in the past, people had always assumed that spiking neural network hardware is not only lower accuracy, it also consumes more energy. But what this paper shows is that with the right data flow, the energy level, the energy gap can be bridged, and in fact, the spiking network can be more efficient as long as you see a high sparsity level, right? And so if you want a high sparsity level, it means we need to invest more in temporally coded SNNs, and we also need to invest in training algorithms that can make these SNNs achieve much higher accuracy. So that's kind of the main take-home message from that work. All right, so this is kind of my closing slide. Right, and so closing slide for the entire lecture series as well, right? And so what we've learned in these 3 lectures is firstly that we've seen a big jump in terms of machine learning hardware in these first few years, right? Even the commercial offerings are giving improvements of 100x, and a lot of that is just coming from customizing for deep networks, right? If you just put in a large number of multiply accumulate units, you can get high throughputs. Scaling helps. And even the networks are now kind of trying to become smaller, right? And so we are also getting some help from the algorithms themselves. And so the next generation hardware needs to kind of look for other opportunities. And there is some low-hanging fruit by doing things like pruning, but then exploiting other approaches for sparsity may cost more. You may need new circuits for in-memory computing. That's another area that has some low-hanging fruit. We've seen that when you're designing chips for training, you need to focus on a good interconnect between the chips. You need to have a lot more memory so that you can save activation maps during the forward pass. I think spiking neural networks do have some potential. So if you're just starting out your PhD and you're looking for topics, I think this is a high risk, high reward topic where I think innovations in training can certainly help both the hardware and the algorithms. All right, so I'll stop there and I'll hang out for the next 15-20 minutes and see if people have questions. And thanks for the time, and thanks for all the great questions that you've had throughout this lecture series. It's been fun to see these questions and answer all of them, even though it has exhausted my voice. All right, thanks everyone, and I'll stick around if you have more questions. So there's a question about how about using different neuron models other than leaky, integrate, and fire, and there's quite a few out there, right? And so definitely LIF has captured most of our attention so far. And so I'm guessing you work in this area, so you're probably familiar with the Ishikevich models, right? And so these are models where people have kind of where neuroscientists have looked at actual neurons and tried to describe them, and they have demonstrated that there are these at least 30 different kinds of behaviors that are exhibited. So there are papers from the IBM True North team that show that with their neuron model, you can actually configure the neurons to emulate each one of these Ishikevich models. right? And sometimes you may need 2 or 3 of their basic neurons to implement one of the Ishikevich neuron models, right? So it is possible, right? And so they're essentially coming up with the basic primitives that use LIF, that use some stochastic features, and using those, they can be configured to do more, right? And I think that seems like a reasonable way to do it. This is kind of like the RISC-CISC approach, right? So one option is to say that there are 30 possible neurons out there. So let me implement a different hardware for each one of those neurons, right? And that would be the CISC approach, where you're implementing a different instruction for every single operation that you can possibly have. Whereas I think the true north approach is more the RISC-like approach, which is saying that I'm going to implement one specific LIF, but it has various configuration parameters. And so I can set them, or I can club together multiple neurons, and that can implement these 30 different neuron types. So that's kind of what they have done. And I think it's a reasonable approach as well. So in some sense, LIF with a few stochastic features is perhaps the way to go. But if you work in this area and have more thoughts, please feel free to share it over here, and we can discuss a little bit more. So there's a question about programmability, and again, I'm not an expert in this space, right? So my students know a lot more about this than I do. And I think there are other groups that do a lot more work in this space, right? So I have a colleague at Utah, Sadeh, who does focus on programmability aspects and compiler aspects. So I'm not a huge expert in this space, right? And so what I'd mentioned even yesterday is that my understanding is that if you try to deploy something on the Google TPU cloud, if you have an implementation of a network in TensorFlow, it's a fairly simple step, to actually do the hardware implementation, right? And so I wish I could say more, but this is kind of the high-level insight I have gathered from my students. So I don't know much else about the programmability and the compiler aspects. So I'll defer to some of the other experts. So question about training. So I didn't quite understand your question. So maybe add a little bit more to give me a little bit more context about what it is that you're concerned about. So the way the landscape works is, we are going to build billions of these chips in the next few years, right? So a large number of those chips are going to be deployed on phones or in a self-driving car and so on, right? And so, if I'm Tesla and I'm building a chip that's going to go in my car, I know that that chip is only going to be doing inference, right? And so, I should build a chip that is focused on inference. Maybe I build something like Simba, right? Where Simba had these relatively small buffer structures. Now, if I took a chip like Simba and tried to deploy it in a Google data center that was doing training, it would behave really badly, right? So Simba, if you look at one of these chiplets, or if you look at one of these packages, the total storage that the entire package has is just a few megabytes, whereas training, needs several megabytes and several gigabytes worth of data, right? So something like Simba would do a really bad job on training, right? And so if I'm Google and I'm trying to build chips that go into my data center for training, I would end up designing a very different chip, right? So that's why I think the field is kind of bifurcated, and you see efforts trying to build efficient inference accelerators and efficient training accelerators, because both have kind of very different requirements. Okay, but if I didn't quite understand your question, please add some more comments and I can take a second stab at it. Yeah, so question about STDP training. And so, yeah, so you are correct that over time, a neuron is getting trained to do what it discovered the first time, right? And in some sense, that's kind of the goal, right? So I'll use a biological analogy over here because I think it is reasonably correct, and I think it'll help you understand this, right? So let's say that initially you have billions of neurons in your brain, and all the weights are random, all right? And suddenly, you see an image of a cat in front of you. Because of those random weights, there are specific neurons that fire, and ultimately there is one neuron that kind of sends a signal wherever saying that I just detected a cat, right? So that initial success of that neuron was just because it had those random weights, right? And what we are trying to do is we are basically saying that I'm going to give you I'm going to give you a reward, right? All the neurons that contributed to me causing neuron number 781 to fire, I'll give you all a reward, right? Because you helped neuron 781 become a cat detector for me, right? So you're essentially kind of doing this reinforcement learning and saying that everybody who contributed to this successful spike, you get a slight bump in your weight, right? So the next time I see the image of a cat, I'm even more likely for neuron number 781 to fire and say, success, I just discovered something that other parts of my brain are now calling a cat, right? So in some sense, STDP is saying that you start out with something that is random, but ultimately what you're trying to do is you're training some neurons to be very good at detecting whatever they detected the first time around, right? So in some sense, it's this is in some sense what unsupervised learning tries to do, right? It's basically saying that each neuron is kind of trying to get clustered. It's trying to it's getting good at it's getting good at detecting a certain pattern. And then there are other parts of the brain that come along and say, oh, looks like this cluster over here, this neuron that detects images that look like this, looks like all of those images look like a cat, or all of those images look like a tree, right? So somebody else comes along and later applies a label to what that neuron became really good at detecting, right? So yes, it is a form of reinforcement learning of whatever random behavior the network was initially doing. Okay, so hopefully that kind of helps explain it. I realize it's a little complicated and a little different from supervised training, using stochastic gradient descent. So so there's a question about frameworks and tools for SNN models, right? And so I had students doing a class project who kind of looked around a lot and finally found something that was good. I don't have the name handy right away. If you can send me an email, I will kind of respond and send you the tools that actually worked out. So I believe Peter Deal, his group has some tools that I think are good. I think there's a tool called Brian. So there are 2 or 3 tools out there, and I'm just forgetting the one that I think my students had the most success with. So if you send me an email, I'll kind of look it up and I'll send that back to you. Okay, but maybe places to look at are Peter Deal's group and Brian. Yeah, so question again about other neuron models and whether that can lead to higher accuracy. And yeah, and I think that's a really interesting space to look at, right? And so when I talk about, the temporal coded SNNs needing better algorithms and, somehow exceeding ANNs, right? Maybe another knob that we can change is the actual neuron model itself, right? So in addition to doing a rate versus temporal, let's change the neuron model and see if that gives us better accuracy. And again, I think that's a good space that I think needs a lot more work. And you're right that if you get that higher accuracy, who cares if you need 3 neurons clubbed together to implement that one neuron model, right? I think that may be a worthwhile trade-off. Yep. Yeah. So question about when I was describing these spiking neural networks and the LIF model, I was kind of staying agnostic about whether this is an analog implementation or a digital implementation. So there are research papers that do both, right? And so, the spinal flow paper that I discussed at the very end, that's a digital implementation. There is also an analog implementation. So, there's another paper from our group called In Excess that uses memristor crossbars to do it. There was a paper at ISCA, at the most recent ISCA from the group in Penn State that was also using analog units to implement a spiking neural network. So this is a paper called Nebula. So you can do implementations in both analog and digital. And again, if you're doing it in analog, even a spiking neural network has weights, right? And those weights are what you would put into each of those resistive elements. So it's just that the inputs are now spikes, which makes life a little bit easier. Even the outputs are spikes, which means that the ADC is just a 1-bit ADC, right? You're just deciding 0 versus 1. And I think in the Nebula paper, they talk about different ways of implementing the sense amplifier. And so that's a good place to look at for an analog design of a spiking neural network. So can something like unsupervised STDP be used to replace backprop, right? And so I think this is a good space, right? So in an earlier slide, I talked about potential use cases for SNNs. And I said that one possible use case is to use SNNs to do the initial training and figure out what the initial weights should be, right? And then you can use backprop to kind of refine those weights and get higher accuracy, right? And so I think a hybrid STDP and backprop does make a lot of sense. It's just an area that I don't think has seen a lot of attention, right? So it might be a good problem to tackle. I don't think it can completely replace backprop, right? I mean, like we will need significant jumps that match the big jumps that backprop has taken in the last 10, 15 years, right? So you may need like an army of people making a lot of progress in the next 10 years. But I think that's a good long-term goal. Yeah, and the similarities between STDP and autoencoders and unsupervised training for ANNs, right? So again, it's a space I have not looked at carefully. So I unfortunately don't have a good answer for you there. Right, but my understanding is that even the unsupervised training, is again a very mathematical process, whereas STDP is much more of a biological and localized training process. And I don't know if people have kind of done a comparative study to say, this is the best this is the best performance that or best accuracy that you can get in each case. So interesting question, but I don't have a good answer for you because I'm not an expert in that space. So yeah, so this is just I guess a mentoring question about my background in academia, right? And again, it I guess it has nothing to do with inference accelerators, which is what you are getting into for your PhD. But I can tell you the story of my PhD and my academic career, and if that helps, then great, right? And so when I started my PhD, I was actually looking at software systems. And it's a topic that I didn't enjoy a whole lot. And, I had a very challenging first year where, I spent the whole year, I didn't make a lot of headway. I struggled to quantify the benefits or the impact that I was having. And so, after the first year, I felt it was a complete failure. And I had a really deep discussion with my advisor. And, there was a new architecture focused project that was starting out at my institution at that time. And so she suggested that I maybe look at that, right? And so I spent an entire summer reading papers on architecture, and that gave me confidence, that gave me the background that I needed. So I had to read about 50 papers, and then I kind of felt that if I came up with an idea, I would know if it was novel, if it was high impact. And so I think that is really where things kind of took off in a good way. And so, my initial PhD was on designing caches, and then I kind of moved into designing a higher ILP single thread core. So it was kind of focused on microarchitecture. And then, once I joined as faculty, I moved into the topic of large cache design and interconnects within those large caches. And then from there, I moved into off-chip memory systems, right? So I was always looking at aspects of the memory hierarchy. And I was always looking for what's the next big bottleneck, and can I come up with ideas that address the bottleneck? And once I solved it, I moved on to the next bigger problem, right? And so I started with small caches, then went to large caches, then went to the external memory system, and then I was not initially planning on getting into accelerators. I could see that the future was there, but it was not a topic that excited me a whole lot at first. But given my interest in memory systems and given my interest in non-volatile memory, when I found out about this analog accelerator, right, this analog circuit that could use a memory system to do computation, that got me interested. And I kind of that was my first paper in the accelerator space, where I basically said that here's an interesting memory circuit that has applications for accelerators. And I, at that point, I got deep enough into data flows and accelerators that I started enjoying it more. And then I spent a few years, I spent the last 5 years looking at this topic, and I've also kind of diversified into accelerators for genomics, right? So that's kind of the story of my academic career. And I guess the take home is that every 4 or 5 years, your interest will change and you'll reinvent yourself. So don't be afraid to do that. And look for big bottlenecks, look for high impact problems. And once you get to the point of being a faculty member, you can even diversify and look at many different problems, right? So I would have probably not looked into spiking neural networks if I didn't have a team of 4 or 5 graduate students, and I could get at least one student to kind of take the high risk and look at spiking neural networks. So I guess one last question: does processing in memory affect the cache and locality efficiency, right? So it does, right? So so if you look at, let's say, the neural cache, right? So one of the so there are, I can interpret your question in multiple different ways, and let me answer each one. So in one example, you can say that the neural cache, does its computations inside the SRAM, right? Which means it does not bring a value into a register and repeatedly reuse it, right? So it's actually losing locality by doing that, right? So it's minimizing data movement, but maybe you get higher efficiency by having some registers next to the SRAM bank, and that's one way of kind of improving locality and improving efficiency. Another way to look at this is to say that when I do processing in memory, suddenly I'm losing cache space for the other thing that the CPU was trying to do, right? And so, yes, there is always going to be that interference. So usually we look at this from the context of, I'm executing a deep neural network. What is the best I can do if I can somehow harness all my resources to execute this deep network, right? So we usually don't talk about the interference among multiple different applications, but that is one example of cache locality and efficiency getting poorer. Okay, and let me know if I didn't kind of get to the heart of your question. So I guess another last question: when you see compute near memory architectures, yeah, so so processing in memory kind of was it saw a lot of activity in the 1990s, and then it was the memory vendors that hesitated and said that processing in memory is just too complicated, it increases cost. It's just not something that is tractable, right? And that's kind of what led to this notion of compute near memory, right? So in this most recent incarnation, people have focused more on saying that, let's not modify the DRAM chips themselves. Let's instead, put some logic that is near the caches, or let's put some logic that's in a 3D stack, right? And so you're not actually messing with the layout of the DRAM arrays themselves, right? And so that's so you have this gradation of, near versus in. And the analog circuits that I mentioned are an example of the in memory, right, where the circuits are part of the arrays themselves, right? So there is this gradation in terms of the benefit that you can get and the risk that it poses to the memory vendors, right? And so I don't have a crystal ball, right? And so it's hard for me to predict exactly where these companies are going. But we've seen a big shift in industry because of these deep neural networks, right? I mean, we've seen all these companies jump in and design these new chips. It has certainly influenced strategy at some of the more traditional companies as well, right? And so similarly, I expect deep neural networks to also influence strategy for the memory vendors as well, right? And so I'm a little bit more hopeful than I was in the past that some of these PIM architectures may actually be realized. And like I mentioned, I think there are some of these startups that are coming out that that are trying to take these analog circuits and make them a commercial reality, right? So I'm kind of missing the names of those companies, but at some point, if you send me an email, I can pass those on to you as well. All right, so I think I'm done with all the questions, and so I'll stop here. Thanks again for the few stragglers that are still hanging around and listening to these last few answers. I had fun doing this, and hope you enjoy the rest of your summer school.